You are listening to Beyond the Mouse, a practical guide to the Linux command line. Like and subscribe to keep up to date on our latest audiobooks. Beyond the Mouse, a practical guide to the Linux command line. Chapter 1, The Hidden Power. Why learn the command line? The first time you open a terminal window, you might be excused for a moment of hesitation. A black or dark screen, just a blinking cursor and some cryptic text, a stark contrast to the colorful, icon-filled world of your desktop. This is the Command Line Interface, or CLI, and it's arguably the most powerful way to interact with your Linux system. But why would anyone choose to type abstract commands when they could just click a button? The answer, as you'll soon discover, is surprisingly compelling. What exactly is the command line? Let's break down the basic components you'll encounter. The terminal. Think of the terminal as the window or application you use. It's the visual interface, the screen where you type your commands and see the computer's responses. It's your communication port. On most Linux distributions, you can usually open it by searching for terminal in your applications menu, or often with a keyboard shortcut like pressing Ctrl, Alt, and the letter T all at the same time. The shell. Once you open the terminal, you're greeted by a shell. The shell is a special program that acts as an interpreter. It takes the commands you type, translates them into something the computer understands, and then carries out your instructions. The most common shell in Linux is called Bash, short for Born Again shell. It's a powerful and versatile language that we'll be learning to speak. The kernel. Beneath the shell and the entire operating system lies the kernel. This is the core of Linux. It's the brain, the central control unit that directly manages your computer's hardware, like memory, processors, and disks. When you type a command into the shell often communicates with the kernel to perform the requested task. So, in simple terms, you type into the terminal, the shell interprets your words, and the kernel actually does the work. Why bother? The compelling benefits of the CLI. It might seem daunting at first, but embracing the command line brings a wealth of advantages. Unmatched efficiency and speed. Imagine you need to rename 100 files in a directory, changing photo_01.jpg to holiday_event_01.jpg, and so on. In a graphical environment, you'd likely write, click each file, select rename, type the new name, and repeat. With the command line, this tedious task can be accomplished with a single command or a short script in mere seconds. Once you know the commands, typing them out is often far quicker than navigating menus and clicking. Automation powerhouse. This is perhaps the command line's biggest superpower. Because commands are text-based, they can be strung together into scripts. Think of a script as a recipe, a list of instructions for your computer to follow, step by step. Want to back up your important documents every night at midnight? Want to automatically delete old log files to save space? Want to process thousands of data files sequentially? All of this and more can be automated with shell scripts, leaving you free to focus on more important tasks. Remote control and server management. Most servers, especially those running in the cloud, don't have a graphical interface. They're managed exclusively via the command line, often using a secure connection called SSH Secure Shell. Learning the CLI allows you to configure websites, manage databases, deploy applications, and troubleshoot issues on powerful remote machines from anywhere in the world, often with nothing more than your laptop and an internet connection. It's like having a universal remote for the internet. Deeper troubleshooting and diagnostics. When something goes wrong with your system or an application, the GUI often provides only a high-level error message. The command line, however, offers a direct window into the system's inner workings. You can inspect log files, monitor running processes, check network connections, and diagnose problems with a level of detail simply unavailable through graphical tools. It empowers you to become your own digital detective. Resource efficiency. Graphical environments consume significant system resources like memory and processor power. The command line, by contrast, is incredibly lightweight. This is why it's the default interface for servers and embedded devices, allowing these systems to dedicate precious resources to their primary functions rather than drawing a fancy desktop. Universal language of Linux. While graphical interfaces can vary wildly between different Linux distributions, like Ubuntu, Fedora, or Mint. The underlying command line tools are remarkably consistent. The ls command you learned today will work the same way on almost any Linux system, server, or even a tiny Raspberry Pi. Your command line skills are truly transferable, making you proficient across the vast ecosystem of Linux. These tools trace their origins back to the foundational Unix operating system of the 1970s, a testament to their enduring utility and power. Your first glimpse. Interacting with the shell. It might seem daunting at first, but taking that first step is easier than you think. Open your terminal window now. You should see something like this. Name your computer name. This is your command prompt. It tells you who you are, typically your username, followed by an @ symbol, and then your computer's network name or hostname. After that, you'll see your current location in the file system, which is home or your home directory, often represented by the tilde symbol, which looks like a squiggly line. Finally, the $sign indicates that you are a regular user. If you ever see a hash symbol hash instead, it means you are the powerful root user with administrative privileges, which we'll discuss later. Now let's type our very first command. Type the word echo, followed by a space, and then type hello command line inside quotation marks. Echo hello command line. That's ECHO, then a space, then the word hello, comma, space, command, space, line, exclamation mark, all inside double quotation marks. Press the enter key. What happened? The command echo simply printed back whatever you typed after it. You should see, hello, command line, congratulations, you just executed your first command. It's a small step, but it shows the direct interaction between you and your machine. Now, let's try another one. Type the letters L followed by S, that's the letter L, followed by the letter SLS. Press enter. The ls command, short for list, will probably show you a list of names. These are the files and subdirectories located in your current working directory, typically your home directory if you just open the terminal. It's like opening a folder on your desktop and seeing its contents, but in text form. You've witnessed the power of direct communication with your Linux system. These simple examples are just the tip of the iceberg, but they demonstrate that the command line isn't a complex puzzle. It's a straightforward, logical way to tell your computer what you want it to do. It might seem like a small leap now, but each step we take together will unlock incredible new capabilities. Remember, the initial strangeness will fade quickly, replaced by a growing sense of mastery and confidence. In the next chapter, we'll dive deeper into navigating your Linux system, understanding where you are, and exploring the files and folders that make up your digital world. Get ready to truly move beyond the mouse. Chapter 2, First Steps, Navigating Your Linux System. In the last chapter, you took your first steps into the command line, understanding the core components, and why this seemingly old-fashioned way of interacting with your computer is incredibly powerful. You even got your hands dirty with your very first commands, echo and ls. Now, it's time to move beyond simply seeing what's around you and start actively exploring. Just like finding your way around a new city, the first skill you need to master in the Linux command line is navigation. The Linux file system, a tree, not a pile. Before we start moving, let's understand the landscape. In Linux, everything starts from a single point, known as the root directory. Think of it as the base of a tree or the top of a family tree diagram. Every other file and directory on your system branches out from this root. This is fundamentally different from systems like Windows, where you might have separate drives like C, D, or E in Linux. All storage devices and partitions are mounted under this single root directory. The root directory is represented by a single /. Underneath the root, you'll find a standard set of directories, each with a specific purpose. We don't need to memorize them all right now, but a few are crucial for everyday navigation. The root directory, everything starts here. Home, this is where personal directories for users are stored. If your username is Alex, your personal directory would be Home Alex. Bin contains essential command line programs, binaries that all users might need, etc., holds system-wide configuration files. Var contains variable data like log files that change frequently. Knowing this basic structure will help you understand where you are and where you need to go. Knowing where you are, the pwd command. Every time you open your terminal, you start in your home directory. This is your personal workspace, typically home/your username. But how do you confirm that? The command pwd, short for print working directory, tells you your current location. Let's try it. Type pwd, and press enter. Pwd. You'll see output similar to this, though your username will be different. Home Alex. This shows your absolute path, meaning the full path, starting from the root directory, all the way to your current location. It's like giving someone your full street address, including the city, state, and country. You are now certain of your position in the file system. Listing contents, revisited. The ls command. In Chapter 1, we briefly used ls to see files. Now, let's explore its power more deeply. Standing in your home directory, type ls again. ls. You'll likely see a list of directories like documents, downloads, pictures, music, public, and perhaps desktop-related folders. These are common directories Linux creates for you. Now, let's make ls work harder. Remember how we used lsl in the last chapter to get a long listing? Let's try that again. Type lsl, ls, space, -l and press enter. lsl. The output is much more detailed, appearing as several columns of information for each file and directory. drwxrxrx 2 Alex students 4096 May 25 10 30 documents. rwrr 1 Alex students 1024 May 24 14 15 mynotes.txt. Let's break down the most important parts of this long listing. First character. The very first character tells you the file type. A D means it's a directory, a folder. A dash means it's a regular file, like a text document or an image. Other characters indicate special types, which you'll encounter less frequently as a beginner. Permissions. The next 9 characters, like rwxrxrx, represent the crucial file permissions, which we'll cover in detail in a later chapter. They control who can read, write, or execute the file. Owner and group. These columns show who owns the file, e.g. Alex, and which group it belongs to, e.g. students. Size. The size of the file in bytes or directory contents for directories. Date and time, when the file was last modified. Name, the actual name of the file or directory. This ls command gives you a concise overview of everything that's going on with your files and folders, providing vital information to manage them effectively. What if you want to see all files, including hidden ones? In Linux, files and directories that begin with a dot are hidden by default. These are often configuration files that you usually don't need to see or interact with. To list them, use the option for all. Type lsa, ls space -a and press enter. lsa. You'll see familiar names, but also new ones starting with a dot, like bashrc, profile, or config. These are important configuration files for your shell and applications. You can also combine options. For example, to see all files, including hidden ones, in a long listing format, you combine A and L. The order of options doesn't matter, so lslaw works just as well as lsal. Type lslaw ls space -la and press enter. lslaw. This is a frequently used combination that gives you detailed information about everything in your current directory. Moving around, the cd command. Now that you know where you are and how to list what's around you, let's start moving. The cd command, short for change directory, is how you navigate the file system. You're currently in Home Alex. Let's move into your Documents directory. Type cd documents cd space documents and press enter. Cd documents. Notice how your command prompt changes. It might now show Home Alex Documents or just ~documents $. This confirms you have successfully entered the Documents directory. You can verify this by typing pwd again. Pwd. The output would be Home Alex Documents. Now, how do you go back up one level to your home directory? Every directory, except the root, has a special entry represented by 2 dots. This means the parent directory, or one level up. Type cd space ... and press enter. cd. Your prompt should change back to reflect your home directory, for example, ~/ or Home Alex. You've successfully navigated back up the tree. Navigating with paths. There are 2 main ways to specify where you want to go with cd. Absolute path. This is the full address starting from the root directory. No matter where you currently are in the file system, an absolute path will take you to that exact spot. Let's say you want to go directly to etc., where system configuration files reside. Type cd etc., cd space / etc. and press enter. Cd etc. You are now in the etc. directory. You can confirm with pwd. Relative path. This path is relative to your current location. You're already in etc. How do you get back to your home directory using a relative path? You could go cd repeatedly until you're back at, then cd home alex. But there's a shortcut. The tilde symbol is a special shortcut that always represents your home directory. No matter where you are in the file system, cd will take you straight back home. Type cd space tilde and press enter. Cd. Your prompt should show you're back in your home directory. Other useful cd shortcuts, cd by itself. If you just type cd and press enter with no arguments, it will also take you back to your home directory. This is often the quickest way home. Cd dash. The dash is a shortcut to go back to the previous directory you were in. If you were in etc., then went to, typing cd would take you back to etc. Your best friend, tab completion. Typing long file and directory names can be cumbersome and prone to typos. Fortunately, the Linux shell has a fantastic feature called tab completion. This is perhaps the single most useful shortcut you'll learn. Here's how it works. When you are typing a command or a file path, type the first few unique letters and then press the tab key. If there's only one possible completion, the shell will automatically fill in the rest of the name for you. If there are multiple possible completions, pressing tab once will do nothing. Pressing tab a second time will show you all the options. You can then type one or two more letters to make your choice unique and press tab again. Let's try an example. Make sure you are in your home directory, cd. Type cd doc, cd space doc. Do not press enter, instead press the tab key. Cd doc then press tab. The shell will likely complete it to cd documents. Notice the trailing slash, which indicates it's a directory. Now you can press enter to go into the documents directory. Now, try this. Go back to your home directory, cd. If you have directories named downloads and documents, type cdd and press tab twice. Cdd then press tab, tab again. The shell will list all options starting with D, perhaps showing documents downloads. Now type O, making it cd do and press tab. It should complete to cd documents because do is unique between documents and downloads. Get into the habit of using tab completion constantly. It will save you immense amounts of time, prevent typos, and help you discover the correct spelling of files and commands. Putting it all together, let's do a quick navigation exercise. Starting from your home directory, find out your current location. You should be in your home directory. pwd. See what's in your downloads directory without leaving your home directory. ls downloads, ls space downloads. Now, move into your downloads directory. cd downloads. List all files, even hidden ones, in a long format in your current downloads directory. lslaw. Go back to your home directory using the shortest command. cd, just cd and enter. Finally, confirm your home, pwd. You've now learned the fundamental skills of command line navigation. Knowing where you are, pwd, seeing what's around you, ls with its powerful options, and moving safely and efficiently between directories, cd. You've also discovered the indispensable power of tab completion. These are the tools you'll use every single day at the command line, forming the bedrock of all your future explorations. In the next chapter, we'll put these navigation skills to even more practical use as we learn how to create, copy, move, and delete files and directories, truly managing your data from the command line. Chapter 3. Understanding Files and Directories, the Linux File System. In the last chapter, you learned how to navigate your Linux system using pwd and cd, and how to list directory contents with ls. These commands are essential, but to truly master them, you need a deeper understanding of the landscape itself, the Linux file system. This chapter will explore the fundamental philosophy of how Linux organizes data, delve into different file types, and clarify how paths work in detail. Everything is a file, the Unix philosophy. One of the foundational principles of Unix-like operating systems, including Linux, is everything is a file. This might sound strange at first, especially when you think about things like printers, keyboards, or network connections. But in Linux, these are often treated as special types of files. You read from them, write to them, and manage them using the same tools you use for regular documents and folders. This elegant simplicity means you can use a consistent set of commands to interact with a vast array of system resources, fostering a powerful and flexible environment. The Linux directory structure. A digital city plan. Remember how we introduced the root directory as the base of the Linux file system tree? Now, let's take a closer look at the key branches and what they represent. Think of the file system as a well-organized city where different districts, directories, have specific purposes. The root directory. This is the ultimate starting point, the foundation of the entire file system. Every file and directory branches off from here. It's the city limits. Bin binaries. Contains essential command line binaries or programs that are available to all users, such as ls, cp, mv, and bash. Think of this as the district housing vital public services. Boot files. This directory holds files necessary for the system to boot up, including the Linux kernel itself. This is the power station of the city. Dev devices. This is where hardware devices are represented as files. Your hard drive, USB drives, keyboard, and webcam might all have corresponding device files here. This is the city's hardware infrastructure, etc. configuration files. This directory is a very important one. It contains system-wide configuration files for almost all programs and services. If you want to change how a program behaves, you often edit a file in etc. This is the city hall, where all the rules and regulations are kept. Home, users' home directories. This is where personal directories for individual users are stored. For example, if you have a user account named Alice and another named Bob, their personal files would be in Home Alice and Home Bob respectively. This is the residential area of the city. Libraries. Contains shared libraries that essential programs need to run. Think of these as the fundamental tools and utility providers that the buildings in bin and other places rely on. Media, removable media, mount point. Often used as a default location where removable media like USB drives or optical discs are automatically mounted when connected to the system. This is the city's bus or train station for visitors. /MNT, temporary mount point. System administrators sometimes use this directory to temporarily mount file systems, such as network shares, when needed. A temporary parking lot. Optional software. Used for installing larger optional software packages that are not part of the standard system distribution. This is like a special industrial park for niche businesses. Process information. A virtual file system that provides information about running processes and kernel statistics. It's not stored on disk like other directories. This is the city's real-time monitoring center. Root user's home directory. This is the home directory for the root superuser. It's separate from home to ensure the root user can log in even if the home partition is unavailable. This is the mayor's private residence, distinct from general housing. SBIN, system binaries. Similar to bin, but contains essential system administration programs that are typically only run by the root user. Think of these as the specialized tools for city engineers. TMP, temporary files, a directory for temporary files created by users and programs. Its contents are often cleared out when the system restarts. This is the city's temporary storage or recycling center. /USR, Unix System Resources. This historically stood for Unix System Resources and contains most user-installed applications, documentation, and source code. Nowadays, it's generally considered read-only by the system administrator after initial setup. This is like the main academic and commercial district. var, variable data. Contains files whose contents are expected to change frequently during normal operation, such as log files, mail queues, and temporary files created by web servers. This is the city's bustling business district, constantly changing. Understanding this structure gives you a mental map of your Linux system, helping you find files, understand their purpose, and troubleshoot issues. Understanding file types from LSL. Recall the LSL command, which provides a long listing. The very first character in the output line tells you the file's primary type. Let's look at an example output again. drwxrxrx 2 Alex students 4096 May 25 10 30 documents. rwrr1 Alex students 1024 May 24 14 15 mynotesdxt. lrwxrwxrwx1 Alex students 10 og 190 link to documents. Documents. Here's what each first character means. D. Directory. This indicates that the entry is a directory or a folder, just like documents. It acts as a container for other files and directories. Regular file. This indicates a regular file, such as a text document like mynotesdxt, an image, a program, or any other standard data file. Most of the files you create will be regular files. L. Symbolic link. This indicates a symbolic link, often called a soft link or symlink. It's essentially a pointer or shortcut to another file or directory. The link to documents line shows that link to documents points to the documents directory. We will explore links in more detail later. There are other less common types like C for character device files, e.g., your keyboard or serial ports, and B for block device files, e.g., hard drives, but you'll mostly encounter D and L in your daily use. You can also use the file command to try and determine a file's type. It inspects the file's contents to make an educated guess. For example, file mynotesdxt might output mynotesdxt, ASCII text, and file /bin/ls might output /bin/ls. ELF 64-bit LSB executable x86 to 64, version 1, SYSV, dynamically linked. This command can be quite insightful in confirming what a file truly is. Absolute versus relative paths, a detailed review. In Chapter 2, we briefly touched upon absolute and relative paths when using CD. Let's refine your understanding, as this concept is fundamental to all command line operations. Absolute paths. An absolute path is like giving a complete address, starting from the root directory. It precisely defines the location of a file or directory, regardless of your current working directory. Example: home/alex/documents/report.txt. No matter where you are in the file system, if you use this absolute path, the system knows exactly how to find report.txt. Relative paths. A relative path defines the location of a file or directory relative to your current working directory. It's like giving directions from where you are standing right now. If you are in home Alex, then documents/report.txt is a relative path to that file. If you are in home Alex documents, then report.txt is a relative path. Single dot represents your current working directory. If you type ls, it's the same as ls. Double dot represents the parent directory, one level up from your current working directory. If you are in home Alex documents, then desktop means the desktop directory that is peer to documents at home Alex desktop. Why both? Absolute paths are great for specifying precise, unambiguous locations, especially when you need to refer to system files or locations outside your immediate vicinity. Relative paths are often quicker to type, more flexible when working within a project structure, and useful within shell scripts that might be run from different starting points. Using tab completion efficiently works with both. A first look at permissions. Who can do what? The LSL output also introduced you to file permissions, those cryptic-looking strings like rwxrxrx. While we'll have a dedicated chapter to permissions later, it's important to understand their fundamental role now. They are crucial for security and controlling access to files and directories on your system. Each set of RWX characters describes an access privilege. R equals read, permission to view the file's contents or list the contents of a directory. W equals write, permission to modify or delete the file or to create delete files within a directory. X equals execute, permission to run an executable file, a program or script, or to enter a directory. These RWX permissions are specified for 3 distinct categories. User owner. The first RWX triplet refers to the file's owner, the user who created it, or who was set as the owner. Group. The second RWX triplet refers to the permissions for the group that the file belongs to. Multiple users can be part of a group, enabling shared access. Others. The third RWX triplet refers to permissions for everyone else on the system who is not the owner and not part of the files group. For example, drwxrxrx for documents. The leading D means it's a directory. RWX for the owner of documents can read, write, and execute enter the directory. RX for the group. Users in the directories group can read and execute enter the directory, but not write to it. RX for others. All other users can read and execute enter the directory, but not modify it. This system ensures that different users can access and interact with files and directories in controlled ways, providing a robust security layer for your Linux system. If you ever try to access a file or directory and get a permission denied error, it's usually because these permissions are set to restrict your access. Building your foundation. By now, you should feel more at home in the Linux file system. You understand its logical hierarchical structure, can identify different file types, and grasp the vital distinction between absolute and relative paths. You've also had your first glimpse into the world of file permissions. These concepts are the bedrock of efficient command line use. With this map of the digital city in your mind, you're now ready to start actively managing its contents. In the next chapter, we'll dive into the hands-on commands that let you create, copy, move, and delete files and directories, putting your navigation skills to practical use. Chapter 4, Creating, Copying, and Deleting, Managing Your Data. In the previous chapters, you've mastered navigating your Linux system and understood its hierarchical structure. You can find out where you are with pwd, list what's around you with ls, and move fluidly between directories with cd. Now, it's time to get hands-on with your data. This chapter will equip you with the essential commands to create, modify, copy, move, and delete files and directories, putting you firmly in control of your digital world. Remember, with great power comes great responsibility, especially when it comes to deleting files. The command line doesn't usually have a recycle bin or trash that you can recover from easily. So, let's learn to manage your data with precision and care. Creating files and directories. Before you can organize anything, you need to create it. 1 mkdir. Making new directories. The mkdir command, short for make directory, is used to create new folders. Let's imagine you're working on a new project for a creative writing class. You want to create a main project folder, and then subfolders for drafts and research. First, make sure you're in your home directory, cd. Now, type mkdir creative writing project, mkdir space creativewritingproject, and press enter. mkdir creative writing project. If you type ls now, you should see your new directory listed. To create the subfolders inside it, you can navigate into the new directory first. cd creative writing project. Now create the subfolders, mkdir drafts, mkdir research. If you ls in your creative writing project directory, you'll see both new folders. What if you wanted to create all of those folders at once, even if the parent folder didn't exist yet? You can use the P option, which stands for parents. This option will create any necessary parent directories along the way. Go back to your home directory, cd, and try this. mkdir p new big project section a subsection 1. Now if you navigate into new big project, cd new big project, then ls, you'll see section A. If you cd section A and ls, you'll see subsection 1. The P option saved you from typing multiple mkdir and cd commands. To touch, creating empty files and updating timestamps. The touch command is primarily used to change the access and modification timestamps of a file. However, if the file doesn't exist, touch will create an empty one for you. This is very useful for quickly setting up placeholder files or testing. Let's create an empty file for your first draft. Make sure you are in your creative writing project drafts directory, cd:/creative writing project/drafts. Type touch first draft txt, touch space first_draft.txt, and press enter. Touch first draft txt. If you ls your drafts directory, you should see first draft txt listed. It's empty, but it's there, ready for you to add content. More on adding content in the next chapter. Copying files and directories, cp. The cp command, short for copy, allows you to duplicate files and directories. It works by taking a source and a destination. 1. Copying a file to a new name in the same directory. Let's say you finished firstdraft.txt and want to save it as reviseddraft.txt before making significant changes, keeping the original intact. Make sure you're in /creative writing project/drafts. Type cp firstdraft.txt reviseddraft.txt. cp space first_draft.txt space revised_draft.txt and press enter. cp firstdraft.txt reviseddraft.txt. Now, if you ls, you will see both files, firstdraft.txt and reviseddraft.txt. They are identical copies. 2. Copying a file to a different directory. You've completed your firstdraft.txt and want to send a copy to your research folder, perhaps to keep it with related notes. Type cp firstdraft.txt. Research cp space first_draft.txt space /research/ and press enter. cp firstdraft.txt research. The research part is a relative path. Remember, means go up one directory level, which brings you to Creative Writing Project, and then research means go into the research directory. If you cd, research, and ls, you'll see firstdraft.txt there. 3. Copying a directory and its contents, cpr. What if you want to copy an entire directory, including all its subdirectories and files? You need to use the R option, which stands for recursive. First, let's create a small directory to copy. Go back to /creative writing project. cd /creative writing project. Now, create a folder called old ideas with a file inside. mkdir old ideas. Touch old ideas /brainstorm.txt. Now, let's copy old ideas to a new directory called archived ideas. Type cpr old ideas archived ideas. cp space -r space oldidEAS space ARCHIVEDIDEAS and press enter. cpr old ideas archived ideas. If you ls now, you'll see both old ideas and archived ideas. You can then cd archived ideas and ls to confirm that brainstorm.txt was copied along with the directory. Without R, cp would have given you an error, saying it could not copy a directory. For interactive copying, cpi. A useful option to prevent accidental overwrites is I, which stands for interactive. If the destination file already exists, cpi will ask you for confirmation before overwriting it. Let's try to copy your firstdraft.txt into the research folder again, even though you already copied it there. Make sure you are in /creative writing project/drafts. Type cp firstdraft.txt /research /firstdraft.txt and press enter. You should see a prompt like this. cp overwrite /research /firstdraft.txt. You can type Y for yes or N for no. Type N and press enter to cancel the overwrite. This simple I option can save you from accidental data loss, moving and renaming files and directories. MV. The MV command, short for move, is used to move files and directories from one location to another. Interestingly, it's also used to rename them. 1. Moving a file to a different directory. This operation works like cut and paste. Your original file disappears from its old location and reappears in the new one. Let's move brainstorm.txt from old ideas to your research folder since it's research-related. Make sure you are in /creative writing project. Type mv old ideas /brainstorm.txt research. mv space oldides/brainstorm.txt space research and press enter. mv old ideas /brainstorm.txt research. Now, ls old ideas will show old ideas as empty, and ls research will show brainstorm.txt alongside firstdraft.txt. 2. Renaming a file or directory. When you mv a file to a new name within the same directory, it effectively renames it. Let's rename firstdraft.txt in your drafts folder to introduction.txt. Make sure you are in /creative writing project/drafts. Type mv firstdraft.txt introduction.txt. MV space FIRST underscore DR a FT dot TXT space INTRODUCTION dot TXT and press enter. MV first draft TXT, introduction TXT. Now LS will show introduction TXT instead of first draft TXT. The content is the same, just the name has changed. This works identically for directories. MV old ideas new ideas would rename the old ideas directory. Like CP, MV also supports the I interactive option to prompt you before overwriting an existing file at the destination. It's a good practice to use it. Deleting files and directories, RM, the dangerous one. The RM command, short for remove, is used to delete files and directories. There is no undo button. When you RM something from the command line, it's typically gone for good. Proceed with caution. 1. Deleting a file, RM. Let's say you've decided you don't need revise draft TXT anymore, as introduction TXT is the way forward. Make sure you're in / creative writing project / drafts. Type RM revise draft TXT, RM space REVISED underscore DRAFT dot TXT and press enter. RM revise draft TXT. If you ls, revise draft TXT will be gone. Forever. 2. Deleting an empty directory, rmdir or rmr. To delete an empty directory, you can use the rmdir command, remove directory. Let's say you want to get rid of archived ideas as you're done with it. First, remove its contents, in this case, just brainstorm TXT. Navigate into archived ideas. CD / creative writing project / archived ideas. RM brainstorm TXT. Now go up one level. CD. Type rmdir archived ideas, RMDIR space ARCHIVEDIDEAS and press enter. rmdir archived ideas. The archived ideas directory should now be gone. 3. Deleting a non-empty directory recursively, rmr. What if a directory contains files or other subdirectories? rmdir would refuse to delete it, giving an error. In such cases, you must use rm with the R recursive option. This tells RM to descend into the directory and delete everything inside it, then delete the directory itself. Let's delete the old ideas directory, which still exists and might contain some remnants. Make sure you are in / creative writing project. Type RMR old ideas, RM space -R space OLDIDEAS and press enter. RMR old ideas. 4. Forcing deletion. RMF and the extremely dangerous RMRF. The F option stands for force. It tells RM to delete without prompting for confirmation, even if files are write protected. This can be combined with R for RMRF. Warning: RMRF is the most dangerous command you can run on a Linux system. Do not type this command lightly, if ever. Let's break down RMRF. RM, the delete command. R, recursive, meaning delete everything within the specified location and its subdirectories. F, force, meaning do not prompt for confirmation. / the root directory. Combining these means, delete everything on my system, starting from the root, and don't ask me if I'm sure. This command will wipe your entire operating system, including all your personal data, critical system files, and everything else. It is used in catastrophic situations or by system recovery tools, but never in general practice. Be very cautious with RMR and RMF. Always double-check what you are deleting. 5. Interactive deletion. RMI. To avoid accidental deletions, especially when using RMR on directories you might be unsure about, you can use the I interactive option. This will prompt you for confirmation for each file or directory before it's removed. Let's create a temporary file and delete it interactively. Touch deleting.txt. RM I deleting.txt. The shell will ask, RM, remove deleting.txt. Type Y for yes or N for no. This RMI approach is a safer way to clean up if you have many files to delete and want to review each one. Symbolic links, shortcuts, not copies, LN. Finally, let's briefly introduce symbolic links, often called symlinks or soft links. Think of them as sophisticated shortcuts to files or directories that can live anywhere on your system. Unlike copying, a symbolic link doesn't duplicate the data. It just points to the original. If you modify the original file, the changes are reflected when you access it via the symlink. If the original is deleted, the symlink becomes a broken link. The command is ln ssource linkname. Let's say you frequently need to access your creative writing project from your home directory, but you don't want to cd all the way into ~documents/projects/creative writing project. You can create a symlink to it directly in your home directory. Navigate to your home directory. cd. Type ln documents creative writing project my novel link. ln space dash s space documents/creativewriting space mynovellink and press enter. ln documents creative writing project my novel link. Now, if you lsl in your home directory, you'll see an entry like this. LRWXRWXRWX 1 Alex Alex 30 OG 1100 my novel link, documents creative writing project. The L at the beginning signifies it's a symbolic link. You can now use my novel link as if it were the actual directory. cd my novel link will take you directly into ~documents/creative writing project. Mastering your files, you now possess the fundamental commands to create, duplicate, move, rename, and delete files and directories. You've also learned the crucial distinction between copying and linking, and hopefully grasped the importance of caution with deletion commands. These tools form the backbone of everyday command line use and are essential for keeping your system organized and efficient. In the next chapter, we'll continue working with files, but instead of managing them, we'll learn how to peek inside, viewing their contents, counting words, and even doing some basic text manipulation. Chapter 5, Peeking Inside, Viewing and Manipulating Text Files. In the last chapter, you learned how to manage your data by creating, copying, moving, and deleting files and directories. Now that you're adept at organizing your digital space, the next crucial skill is knowing how to inspect the contents of your files. Many important files in Linux, from system configuration to log outputs, are plain text. This chapter will introduce you to a suite of powerful command line tools designed for viewing and performing basic manipulations on text files without ever needing to open a graphical text editor. Viewing entire files. Cat, the cat command, short for concatenate, is one of the simplest ways to display the contents of a file directly to your terminal screen. While its primary purpose is to join files together, its most common use is to quickly display a single file. Let's imagine you've created a simple text file named mynotesTxt. You can create one now by going to your home directory, cd, and typing echo, this is the first line, mynotesTxt. Echo, this is the second line, mynotesTxt. We'll explain what the and symbols mean in a later chapter. For now, just know they put the text into the file. Now, to display the contents of mynotesTxt, simply type cat followed by the file's name, cat mynotesTxt. That's cat space my_notes.txt. The output on your screen will be, this is the first line, this is the second line. Cat is great for small files that fit entirely on your screen. However, you'll quickly discover its limitation when dealing with larger files, as the content will simply scroll by too fast to read. Viewing large files paginated, less and more. For longer files, you need a way to view their content page by page or screen by screen. This is where less and more come in. 1. More, the older pager. The more command is the older of the two pagers. It displays content one screen at a time, allowing you to advance through the file. Let's imagine you have a very long log file, perhaps /var/log/syslog, a common system log that records various system events. You likely don't have write access to create it, but more can read it. Type more var/log/syslog, more space/var/log/syslog and press enter. More var/log/syslog. The file will appear, filling your terminal screen. At the bottom of the screen, you'll see a more prompt, possibly with a percentage indicating how much of the file you've viewed. To navigate, press spacebar to move forward one screen at a time. Press enter to move forward one line at a time. Press Q to quit and return to your command prompt. You cannot go backward with more. 2. Less, the modern pager. The less command is more powerful and flexible than more. Despite its name, less allows you to navigate both forward and backward through a file and even search within it. It's the preferred pager for most Linux users. Let's view the same syslog file with less var/log/syslog. The file will load, similar to more. The prompt at the bottom will reflect the file name. To navigate within less, press spacebar to move forward one screen. Press Enter to move forward one line. Press B to move backward one screen. Press D to move backward half a screen. Press Q to quit. To search forward through the file, press /, then type your search term e.g. error and press Enter. Press N, next, to jump to the next occurrence of your search term, or N, capital N, to jump to the previous occurrence. To search backward, press ? Then type your search term and press Enter. Less is incredibly versatile and useful for examining logs, large configuration files, or any text file that won't fit entirely on your screen. Viewing portions of files, head and tail. Sometimes you don't need to see the whole file, just the beginning or the end. This is particularly useful for log files, where the most recent entries are often at the end. 1. Head beginning of a file. The head command displays the first few lines of a file. By default, it shows the first 10 lines. Let's try it on our mynotesTXT file if you added more lines. Head mynotesTXT. If you wanted to see, say, only the first 3 lines, head n3 mynotesTXT. That's HEAD space dash n space 3 space my underscore notes dot txt. 2. Tail end of a file. The tail command displays the last few lines of a file. By default, it also shows the last 10 lines. This is much more commonly used than head, especially for monitoring active logs. Tail mynotesTXT. To see, for example, the last 15 lines, tail n15 mynotesTXT. 3 tail f follow a file. This is one of the most powerful uses of tail. The f option, for follow, tells tail to continuously output new lines as they are added to the file. This is indispensable for real-time monitoring of log files. Imagine you're troubleshooting a program, and its log output is continuously updated. You can open a second terminal window and run tail f on its log file. Tail f var/log/syslog. Now, as new events happen on your system and get written to syslog, you will see them appear instantly in your terminal, without having to rerun the command. To stop tail f or any command that is continuously running, press Ctrl+C basic text processing. WC sort unique. Beyond just viewing, the command line offers tools for simple yet powerful text manipulations. 1. WC word count. The WC command for word count can count lines, words, and characters in a file. Using mynotesTXT, WC mynotesTXT, the output might be 2:1046 mynotesTXT. This means 2 lines, 10 words, 46 characters. You can also specify what you want to count. WCL mynotesTXT, only lines. WCW mynotesTXT, only words. WCC mynotesTXT, only characters. 2 sort ordering lines. The sort command puts the lines of a text file into alphabetical or numerical order. Let's create a file called names.txt. Echo Charlie names.txt. Echo Alice names.txt. Echo Bob names.txt. Echo Alice names.txt. Now sort it, sort names.txt. The output will be Alice, Bob, Charlie. Sort has many options, including sorting numerically N, reversing order R, and sorting by specific columns more advanced. 3. Unique remove duplicate lines. The unique command filters out repeated lines in a file. Importantly, unique only detects consecutive duplicate lines. This means you often use it in combination with sort to ensure all duplicates are adjacent before unique processes them. Let's use our names.txt after sorting it. First, display names.txt again so you remember it has 2 Alice entries. Cat names.txt. Charlie, Alice, Bob, Alice. Now, let's try cat names.txt unique. Cat names.txt unique. We'll learn about the symbol, called a pipe, in the next chapter. For now, it means take the output of cat names.txt and feed it as input to unique. The output is Charlie, Alice, Bob, Alice. Notice Alice still appears twice. This is because the two Alice lines were not consecutive in the original names.txt file. Now, let's use sort first to make them consecutive, then unique. Sort names.txt unique. The output, Alice, Bob, Charlie. Success, the duplicate Alice line has been removed. You can also use unique, C, to count how many times each unique line appears. Sort names.txt unique C. Output, 2 Alice, 1 Bob, 1 Charlie. Echo revisited, more than just printing. You used echo in Chapter 1 to print hello, command line. Echo is fundamentally about displaying text, but it's also incredibly useful within shell scripts or when combined with other commands to generate output that can then be processed. It takes whatever arguments you give it and prints them to the standard output, usually your terminal screen. We'll see echo used extensively as we delve into scripting. The power of text utilities. The commands covered in this chapter, cat, less, more, head, tail, wc, sort, unique, and echo, are some of the most frequently used tools on the Linux command line. They allow you to quickly inspect, filter, count, and reorder text data directly in your terminal, making you highly efficient in managing everything from configuration files to extensive log outputs. In the next chapter, we're going to unlock even more potential by learning how to search within those files and how to combine commands using redirection and pipes to create incredibly powerful custom workflows. Chapter 6. The Art of Searching, Finding Files and Content. So far, you've learned how to organize your files and even take a peek inside them to read their contents. But what happens when your collection of files grows to hundreds or thousands? Or when you wrote something important but can't remember which file you saved it in? This is where the true power of the command line shines. Its ability to search quickly and precisely, finding needles in digital haystacks. This chapter will introduce you to two incredibly powerful tools for searching. Find, for locating files and directories, and grep, for searching within their contents. Finding files by name and more. The find command. The find command is your digital detective, capable of scouring your file system for files and directories that match specific criteria. It can search by name, type, size, modification date, ownership, and much more. The basic structure of a find command is find starting point, options expression. The starting point tells find where to begin its search. A single dot means start in the current directory. A // means start from the root directory. Be cautious, this can take a long time and generate a lot of results on a large system. Let's go back to Alex's creative writing project. Navigate there using cd:/creative writing project. 1. Finding by name. Alex remembers they wrote a file called charactersketches.txt, but they can't remember if it's in drafts or research or somewhere else within the project. They can ask find to look for it. Type find. Name charactersketches.txt, find space dot space dash name space double quote char a cter underscore sketches dot txt double quote and press enter. Find name charactersketches.txt. If Alex has that file in, say, the research subdirectory, the output might be /research/charactersketches.txt. The / indicates that the file was found within the current directories tree. Using wildcards, the name option works beautifully with wildcards, special characters that represent patterns. Asterisk matches any sequence of 0 or more characters. Question mark matches any single character. Alex is looking for all their draft files, which are named like draftdv1, txt, draftdv2, txt, etc. Type find name draftdv. txt, find space dot space dash name space double quote draft underscore v question mark dot txt double quote and press enter. Find name draftdv, txt. This would find draftdv1, txt, draftdv2, txt, but not draftfinal.txt. If Alex wanted all files starting with draft and ending with txt, they could use find name draft.txt. This would include draftdv1, txt, draftdv2, txt, and draftfinal.txt. Remember to use quotation marks around patterns with wildcards to prevent the shell from expanding them before find sees them. 2. Finding by type. You can specify if you're looking for files or directories. F Regular file. D. Directory. To find all directories within your current project, find, type D. To find all regular files, find. Type F. 3. Finding by size. This option lets you search for files larger than, smaller than, or exactly a certain size. C. Bytes. K. Kilobytes. M. Megabytes. G. Gigabytes. Use plus for greater than, for less than. Alex wants to find any large images they've downloaded for research, say, larger than 5 megabytes. Find. Type F size plus 5M. 4. Finding by modification time, M time. This is incredibly useful for finding recent files or old archives. M time refers to modification time in days. N. Files modified within the last N days. Plus N. Files modified more than N days ago. N. Files modified exactly N days ago. Be careful, this is exact. Alex needs to quickly find all files they've worked on in the last 7 days. Find. Type F M time minus 7. This finds files that were modified less than 7 days ago, including today. 5. Performing actions with find brief mention. While find is primarily for finding, it can also execute commands on the files it finds. For example, find. Name, back, delete would find all files ending with back and delete them. However, commands like delete can be very powerful and destructive if used carelessly. We will explore performing actions on find results in more detail when we discuss pipelines and zargs in the next chapter. Searching inside files. The grep command. You briefly met grep in Chapter 5 when we chained it with sort and unique. Now, let's explore grep's core purpose, searching for specific text patterns within the contents of files. The name grep stands for Global Regular Expression Print. The basic structure of a grep command is grep options, pattern file. Let's assume Alex has a few draft files draftdv1, txt, draftdv2, txt, and draftfinal.txt within the draft subdirectory of their creative writing project. Alex wants to find every mention of a character named Alara. Navigate to / creative writing project / drafts. Type grep Alara draftdv1, txt grep space double quote elar a double quote space dr a ft underscore v1 dot txt and press enter. Grep Alara draftdv1 txt. If Alara is mentioned, grep will print every line from draftdv1 txt that contains the text Alara. Useful grep options. Grep has many powerful options to refine your searches. I ignore case, matches Alara, ELARA, etc. Grep Alara, draftdv1 txt. N line number shows the line number where the match was found. Grep N Alara, draftdv1 txt. Output might be 5. The ancient elf Alara walked into the tavern. V invert match only shows lines that do not contain the pattern. Useful for filtering out irrelevant information. Grep V chapter, draftfinal.txt. This would show all lines that are not chapter headings. W whole word matches the pattern only if it's a whole word. So car won't match cartoon. Grep W plot research.txt. R recursive searches through subdirectories. If Alex wanted to search for Alara in all files within the creative writing project and its subfolders, they could use grep R Alara. This is very common when searching for text in an entire project directory. Searching multiple files with wildcards. You can use wildcards directly with grep to search multiple files. To find Alara in all txt files in the current drafts directory, grep Alara, txt. This tells grep to search all files ending with txt. A taste of regular expressions. The power of patterns. Grep's true power comes from its ability to use regular expressions, or regex. A regular expression is a sequence of characters that defines a search pattern. It's like an advanced wildcard system that lets you specify complex text structures. Learning full regex is a subject for an entire book, but here are a few fundamental patterns commonly used with grep. Caret matches the beginning of a line. Example, grep chapter mynovel.txt will find lines that start with chapter. $$ matches the end of a line. Example, grep the end $mynovel.txt will find lines that end with the end. Dot matches any single character. Example, grep gry colors.txt will match gray, grby, etc. Asterisk matches 0 or more occurrences of the preceding character or group. Example, grep goggle words txt will match jiggly, goggle, google, guoggle, etc. Dot asterisk matches any sequence of 0 or more characters. This is a very common and powerful combination. Example, grep startend document txt finds lines that contain start, followed by any characters, followed by end. Square brackets matches any single character within the brackets. Example, grep eu mytext txt will find lines containing any vowel. You can also specify a range. Grep am mytext txt finds lines with any lowercase letter from a to m. To use extended regular expressions, which include more powerful features like plus for 1 or more, or for 0 or 1, you'll often need to use grep e or the egrep command. For most common tasks, basic grep with the patterns above is sufficient. Combining find and grep. The search synergy. While find locates files and grep searches within them, they are often used together to achieve even more precise results. Imagine Alex wants to find all their markdown files, MD, that contain the phrase, world building. They could first use find to get a list of all, MD files, and then feed that list to grep. This combination is typically achieved using a concept called pipelines and the zargs command, which we will dedicate the entire next chapter to. For example, a command to achieve the above might look like find, name MD, print 0 zargs -0 grep, world building. Verbalizing this, it means find files in the current directory ending in MD and print their full names one per line, separated by null characters. Then take that list of file names and use it as input for grep, which will then search each of those files for the phrase, world building. Don't worry if that last command looks complex. It's just a preview of the incredibly powerful concepts that you'll master in the next chapter. The ability to chain commands together using redirection and pipes is truly what transforms a collection of simple utilities into a formidable toolkit for any task. Unleashing your inner search engine. You now have the fundamental tools to become a master searcher on your Linux system. Find helps you locate files and directories based on their metadata and location, while grep allows you to delve into their content with powerful pattern matching, including regular expressions. The more you use these two commands, the more intuitive they will become, saving you countless hours wading through directories and manually inspecting files. In the next chapter, we'll dive deep into redirection and pipes, the glue that connects different commands and unlocks an exponential increase in your command line power. Get ready to build your own custom data processing workflows. Chapter 7, Connecting the Dots, Redirection and Pipes. In the world of the command line, individual commands are like specialized tools. ls lists, cat displays, grep searches, and wc counts. Each does one job well. But the real magic, the true power that transforms simple utilities into a formidable workflow, comes from their ability to interact with each other. This is achieved through redirection and pipes, mechanisms that allow commands to share data seamlessly. Think of it as building a flexible manufacturing pipeline out of modular components. Standard streams, where data flows. Before we dive into redirection, let's understand how commands typically communicate. Every command, by default, has 3 standard data channels, or streams. Standard input, stdin. This is where a command expects to receive its input. By default, stdin is connected to your keyboard. When you type commands, their input comes from what you're typing. Standard output, stdout. This is where a command sends its normal output. By default, stdout is connected to your terminal screen. When ls lists files, its output appears on your screen. Standard error, stdir. This is where a command sends its error messages. By default, stdir is also connected to your terminal screen, but it's a separate stream from stdout. This distinction is important for more advanced scripting and command chaining. Redirection and pipes allow you to change these default connections, making the output of one command the input of another, or sending output to files instead of the screen. Redirecting standard output. And the most common form of redirection involves sending a command's standard output, stdout, to a file instead of displaying it on the screen. 1. Overwriting redirection. Sending output to a file. The single greater than sign tells the shell to take the stdout of the command on the left and write it into the file specified on the right. Crucially, if the file already exists, it will be completely overwritten. Let's say you want to save a list of your home directory's contents to a file. Navigate to your home directory, CD. Type lsl home contents.txt, ls space dash l space greater than sign space home underscore contents dot txt and press enter. lsl home contents.txt. You won't see any output on your screen from lsl. Instead, if you now type cat home contents.txt and press enter, you'll see the detailed list of your home directory's contents saved in that file. 2. Appending redirection, adding output to a file. The double greater than sign works like, but with a crucial difference. It appends the stdout to the end of the file if the file already exists, rather than overwriting it. If the file doesn't exist, it will create it just like. Let's add the current date and time to home contents.txt. Type date home contents.txt, date space double greater than sign space home underscore contents dot txt and press enter. Date home contents.txt. Now, if you cat home contents.txt, you'll see the long lsl output, followed by the current date and time on a new line at the very end. This is excellent for building log files or collecting data over time. 3. Redirecting standard error. 2. Capturing error messages. Sometimes, you want to capture only the error messages generated by a command. Perhaps because the command's normal output is too verbose, or you want to log errors separately. The stdir stream is assigned file descriptor number 2, so we use 2 to redirect only stdir. Let's try to list a directory that doesn't exist and capture its error message. lsl non-existent directory, 2 errors log. You might not see anything on screen for errors. Now, cat errors log will show you something like ls cannot access non-existent directory. No such file or directory. This is powerful for troubleshooting scripts or long-running processes, allowing you to separate success messages from failure messages. 4. Redirecting both standard output and standard error, and/or filename 2 and 1. Often, you want to capture both the normal output and any error messages into a single file. There are 2 primary ways to do this. The classic way, filename 2 and 1. This reads as redirect standard output to filename, then redirect file descriptor 2, standard error, to the same place as file descriptor 1, standard output. It's important that 2 and 1 comes after filename, otherwise, stdir would be redirected to the original stdout, the screen, not the file. lsl non-existent directory, combined output log 2 and 1. The modern bash way, and this is a simpler, more concise syntax for bash shells. lsl non-existent directory and combined output log. Both commands will send whatever lsl non-existent directory prints to both stdout and stdir into the combined output log file. Redirecting standard input. While less commonly used directly for interactive commands, you can also redirect a file's contents into a command's stdin using the less than sign. This is useful for commands that are designed to process input from stdin, but you want them to process a file instead. Let's use the sort command. Normally, sort with a file name acts directly on the file, e.g., sort names.txt, but you can explicitly feed it with type sort names.txt, sort space less than sign, space names dot txt and press enter. Sort names.txt. This will sort the lines as if you had typed them directly into sort. Pipes, connecting commands. This is where the real power lies. A pipe, represented by the vertical bar, takes the standard output stdout of the command on its left and feeds it directly as the standard input stdin to the command on its right. It's like a digital conveyor belt, streaming data from one process to the next without touching your screen or an intermediate file. Let's review some examples from previous chapters and introduce new ones, now with a full understanding of the pipe. 1. Paging long output. You learned that lsl can produce a very long list. You also learned that less can paginate output. Let's combine them. lsl etc. less. This command means take the detailed list of files in the etc. directory, lsl etc., and instead of showing it on my screen, send it as input to the less command, which will then allow me to scroll through it page by page. This is a fundamental workflow on the command line. 2. Finding processes or anything else. Remember ps-aux to list all running processes, and grep to search text. Maybe you want to see if the Firefox browser is currently running. ps-aux grep Firefox. This means list all running processes with detailed information, ps-aux, then take that giant list and feed it as input to grep, which will then filter that list, showing only the lines that contain the word Firefox. 3. Counting specific files with wc. Perhaps you want to count how many configuration files are in etc. that end with conf. ls etc. grep conf wcl. Breaking this down, ls etc. lists all files and directories in etc. Takes that list and sends it to grep. Grep conf filters the list to show only items containing conf, takes that filtered list and sends it to wc. wcl counts the number of lines, which represents the number of files ending with conf. This shows how you can chain multiple commands to perform complex data transformations. 4. Find, zargs, and grep. The ultimate search combo, revisited. In Chapter 6, we briefly mentioned combining find and grep to search files by content. Find outputs file names, but grep expects file names as arguments, not from stdin. This is where zargs comes in. Zargs is a command that reads items from standard input and then executes another command using those items as arguments. Let's find all txt files in your creative writing project that mention the word universe. Navigate to /creative writing project. Find, name, txt, print 0, zargs -0 grep universe. Let's decipher this powerful pipeline. Find, name, txt, print 0, find all files ending with txt in the current directory and its subdirectories. The print 0 option is crucial here. It tells find to separate its output file names with a null character instead of a new line. This is important because file names can contain spaces, and a newline separator would break a single file name with spaces into multiple arguments. Takes the null-separated list of file names from find and pipes it to zargs. Zargs -0 reads the null-separated input from find. The corresponding option tells zargs to expect null-terminated input. Grep universe. This is the command that zargs will execute. Zargs will take the file names it receives and pass them as arguments to grep, so grep will perform the search on each of those files. This common find zargs grep pattern is a staple for powerful command line text processing and search tasks. It demonstrates the incredible flexibility of the shell to combine simple tools into highly sophisticated workflows. The T command, output to screen and file. The T command is a special utility that reads standard input and then writes it to both standard output, your screen, and one or more files. It's particularly useful when you want to see the output of a command as it's happening, but also save it to a file for later review. Think of it like a T pipe fitting, splitting the flow. You can use the redirection operators or with T to overwrite or append to a file. Let's perform an lsl command, show its output on screen, and also save it to dirlisting.txt. lslt dirlisting.txt. You'll see the lsl output on your screen as normal. In addition, the same output has been saved to dirlisting.txt. If you then cat dirlisting.txt, you'll see it. To append to an existing file, use a with T. Date T a dirlisting.txt. This will show the current date on your screen and append it to dirlisting.txt. T is invaluable for logging shell sessions or capturing the output of long-running commands, offering both real-time visibility and persistent storage. Connecting the dots, unleashing the power. Redirection and pipes are the true game changers on the command line. They elevate your interaction beyond single commands and allow you to chain operations into complex, efficient, and automated workflows. The ability to route data flows between different commands is a cornerstone of Linux system administration, scripting, and data processing. You now have the fundamental building blocks to craft powerful command pipelines. In the next chapter, we'll delve into more advanced file system tools, building upon your newfound mastery of command chaining to tackle more robust data management tasks. Chapter 8, Becoming a Power User. Advanced File System Tools. You've learned the bedrock of command line interaction, navigating, managing files, viewing content, and even searching within files. Now, with your mastery of basic commands and the powerful art of pipes and redirection, you're ready to wield more sophisticated tools. This chapter will introduce you to commands that help you manage disk space, understand file linking in more depth, and efficiently bundle and compress your data, moving you firmly into the realm of the Linux power user. Understanding disk usage, DF and do. Knowing how your disk space is being used is crucial for system health and performance. Linux offers two primary commands for this: df, disk-free, and do, disk usage. While their names sound similar, they serve different purposes. 1 df, reporting file system usage disk-free. The df command tells you about the overall disk space usage of your mounted file systems. Think of it as looking at how much total capacity your hard drive partitions have and how much of that is currently occupied. Type df, d, f, and press enter. df. You'll typically see a table of output with columns like file system, 1K blocks, used, available, use percent, mounted on. The 1K blocks column often shows sizes in 1 kilobyte blocks, which can be hard to read. For a more human-readable output, use the H option, DFH. Now the sizes will be displayed in gigabytes, G, megabytes M, or kilobytes K, making them much easier to understand. For instance, you might see dev/sda1 is 40G 40 gigabytes, with 20G used and 18G available, at 55% use percent, mounted on the root file system. DFH is your go-to command for quickly checking how much free space you have on your main system drive or any other mounted drives like external hard disks. 2. Do. Estimating file and directory space usage, disk usage. In contrast to DF, which reports on entire file systems, do is used for understanding how much disk space specific files or directories are consuming. Think of do as going into a specific folder and summing up the sizes of everything inside it. Let's go back to your creative writing project directory, cd/creative writing project. Type do and press enter. Do. By default, do will print a line for every subdirectory and file, showing its size in 1 kilobyte blocks, followed by the name. This can be very verbose for large directories. To get a human-readable summary of the current directory's total size, use a combination of S, summary, and H, human-readable. Do sh. This will give you a single line of output, like 24M, indicating that your current directory and everything inside it are taking up 24 megabytes. If you want to see the sizes of subdirectories within your current location, but not their individual files, use do-h. Do-h. This will show something like 4.0K drafts, 8.0K research. 24mdo is your primary tool for finding out which files or subdirectories are consuming the most space, especially when you notice your hard drive getting full and you need to free up space. Links revisited, hard links versus symbolic links, LN. In Chapter 4, you briefly encountered symbolic links, LNS, as a way to create a shortcut to a file or directory. Now let's delve deeper into both symbolic and hard links, which are two different ways to refer to the same underlying data on your disk. 1. Symbolic links, soft links, LNS. What they are: a symbolic link or soft link or symlink is a special type of file that contains a text string which is the path to another file or directory. The system then redirects any operations on the symlink to that target path. Analogy. Think of a symbolic link as a signpost or a Google Maps shortcut. It doesn't contain the destination itself, just directions to it. If the original file or directory is moved or deleted, the symbolic link breaks, becoming a dangling pointer that points to nothing. Key characteristics: can point to files or directories, can span across different file systems, e.g., a link on your main hard drive pointing to a file on a USB stick. If the original is deleted, the link becomes invalid. They have a different inode number, a unique identifier for files on a file system. Example from Chapter 4, LNS Documents Creative Writing Project My Novel link. When you listed it with LSL, you saw the L at the beginning and the pointing to the original. 2 hard links, LN without S. What they are: a hard link is a directory entry that directly points to an existing file's underlying data on the disk. Essentially, it's another name for the exact same file. When you create a hard link, it increases the link count of the original file. Analogy: think of a hard link as a different physical nameplate on the same house. The house itself exists independently of any single nameplate. If you remove one nameplate, the house and its other nameplates remain. Only when the last nameplate is removed, when the link count reaches 0, is the house, the data, actually removed. Key characteristics: can only link to files, not directories. Must reside on the same file system as the original file. Deleting the original file does not delete the data until all hard links to it are also removed. They share the same inode number as the original file because they are the original file. Example usage: let's create a hard link to mynotes.txt, which you should have in your home directory. Navigate to your home directory, cd, ln mynotes.txt lecture notes.txt. Now, if you lsl for both files, lsl mynotes.txt lecture notes.txt, you'll see something like rwrr2 alex 46 og 1015 30 mynotes.txt, rwrr2 alex 46 og 1015 30 lecture notes.txt. Notice the number 2 in the third column. This is the link count, indicating that there are 2 hard links, names pointing to this data. If you delete mynotes.txt, rm mynotes.txt, lecture notes.txt will still exist and contain all the original data, and its link count will drop to 1. When to use which? Symbolic links are more common and flexible. Use them when you need shortcuts that can point across different drives or to directories, or when you want the link to break if the original is gone. Hard links are useful for specific scenarios like ensuring a file always has at least one reference, e.g., in version control systems, or for creating multiple names for a file without consuming extra disk space. Compression and archiving, bundling your data. When you have many files you want to bundle together for easy transfer, or if you need to save disk space, compression and archiving are key. 1. gzip and gunzip. Single file compression. Gzip, GNU-zip, is a popular compression utility for single files. It creates files with a GZ extension. Gunzip is used to decompress them. Let's compress home contents.txt that you created in Chapter 7. Navigate to your home directory, cd, gzip home contents.txt. If you ls now, you'll see home contents.txt gz, and home contents.txt will be gone. Gzip typically replaces the original file with the compressed version. To decompress it, gunzip home contents.txt gz. The file will be restored as home contents.txt. 2. bzip2 and bunzip2. Alternative compression. bzip2 is another compression method, often offering better compression ratios than gzip, meaning smaller file sizes, but it's generally slower. It creates files ending in bz2. To compress, bzip2 mynotes.txt creates mynotes.txt bz2. To decompress, bunzip2 mynotes.txt bz2 restores mynotes.txt. 3. Zip and unzip. Cross-platform archives. For creating archives that are easily compatible with Windows or Mac OS systems, the zip utility is your friend. It combines archiving, bundling multiple files, and compression into one step. Let's say you want to zip up your creative writing project to share with a friend. Navigate to its parent directory, e.g., CD documents. To zip a directory, zip r creative writing project zip, creative writing project. This is zip space dash r space CRE a T I V E underscore WRIT ING underscore PROJEC. T.zip space CRE a T I V E WRIT ING PROJECT. The R option is crucial for recursive, meaning it includes all subdirectories and files within Creative Writing Project. To unzip the archive, unzip Creative Writing Project zip. This will extract the contents into a new Creative Writing Project directory in your current location. 4. tar. The tape archiver and its compressed forms. Tar, originally short for tape archiver, is the traditional Unix utility for bundling multiple files and directories into a single archive file, a tarball. It primarily archives, it doesn't compress by default. However, it's almost always used in conjunction with compression programs like gzip or bzip2 to create targz, tgz, tarbz2, or tarxz files. The tar options you'll use most often: C. Create a new archive. X. Extract files from an archive. V. Verbose output show the files being processed. F. Specify the file name of the archive. This option must be followed immediately by the archive file's name. Z. Use gzip compression for targz or tgz. J. Use bzip2 compression for tarbz2. J. Use xz compression for tarxz. Usually tarxz compression is highly efficient but slower. Creating a compressed tarball e.g. targz. Let's create a gzip compressed tarball of your creative writing project directory. Ensure you are in the parent directory, CD Documents. tar czvf creative writing project targz, creative writing project. That's TAR space dash CZVF space CREATIVE underscore WRITING underscore PROJECT dot TAR dot GZ space CREATIVEWRITING PROJECT slash. Breakdown. C. Create, Z. gzip, V. verbose, F. file followed by archive name, then the directory to archive. Extracting from a compressed tarball. To extract the files from creative writing project targz, ensuring you're in the desired destination directory, e.g., an empty directory you just created. tar xcvf, creative writing project targz. Breakdown, X extract, Z gzip, V verbose, F file, followed by archive name. tar is the Swiss Army knife for archiving and is incredibly common for distributing software, backups, and large collections of files in the Linux world. The Power Users Toolkit. You've now added significant tools to your command line arsenal. df gives you the big picture of disk space, while do helps you pinpoint where space is being consumed. Understanding hard and symbolic links expands your file management capabilities. And mastering tar, gzip, and zip allows for efficient bundling and compression of your data. These commands are indispensable for maintaining a healthy and organized Linux system. In the next chapter, we'll shift our focus from file management to process management, learning how to inspect and control the applications and tasks running on your system. Chapter 9, Managing Processes. What's running on your system? Up to this point, we've focused on static elements of your Linux system, files, directories, and their organization. But a powerful computer is a dynamic entity, constantly running numerous programs and services. These running programs are called processes. Understanding how to view, monitor, and manage these processes is a crucial skill for any Linux user, enabling you to troubleshoot unresponsive applications, monitor system resource usage, and even run tasks efficiently in the background. What is a process? Simply put, a process is an instance of a running program. When you launch a web browser, that's a process. When your operating system starts up, it launches many processes in the background to handle tasks like networking, logging, and managing user logins. Each process is assigned a unique identifying number called a process ID or PID. Processes often have parent-child relationships. When you launch a command in your terminal, the terminal is the parent process, and your command becomes a child process. Viewing processes, PS and top. There are several commands to inspect running processes. 1. PS, Process Status Snapshot. The PS command, Process Status, gives you a static snapshot of the currently running processes. It doesn't update automatically, it just shows you what was running at the exact moment you executed the command. Type PS, PS, and press Enter. PS. You'll likely see a very short list, probably just your current shell, e.g., bash, and the PS command itself. This is because, by default, PS shows only the processes associated with your current terminal session. PID TTY times CMD 1234 PTS/0000 bash 5678 PTS/0000 PS. To get a more comprehensive view of all processes running on your system, you'll need to use PS with options. The most common and useful combination, especially on Linux, is PSOX. PSOX PS space AUX. Let's break down these options. A. Show processes for all users. U. Display more detailed, user-oriented information, like who owns the process, CPU memory usage. X. Show processes that are not attached to a controlling terminal, daemon processes, system services. The output of PSOX will be a long, detailed list, often requiring you to pipe it through less to view it, PSOX less. You'll see columns like user, the user who owns the process, PID, the unique process ID, %CPU, the percentage of CPU time the process is currently using, %MEM, the percentage of physical memory the process is using, VSZ, virtual memory size, RSS, resident set size physical memory used, TTY, the controlling terminal or, for processes not attached to one, stat, current process status, e.g. R for running, S for sleeping, Z for zombie, T for stopped. Start, the time the process started. Time, total CPU time consumed by the process. Command, the command that launched the process. This command is invaluable for seeing what's running, who owns it, and how many resources it's consuming. For example, if your computer is running slowly, you might spot a process consuming 99% CPU. 2 top, real-time process monitoring. While PS gives you a snapshot, top table of processes provides a dynamic, real-time view of your system's processes, updating the display every few seconds. It sorts processes by CPU usage by default, making it easy to identify resource hogs. Type top T, O, P, and press Enter. Top. Your terminal will become an active display showing System Summary. At the top, you'll see a summary of your system's uptime, number of users, load average, system activity over 1, 5, and 15 minutes, task summary total, running, sleeping, stopped, zombie processes, CPU usage percentages, and memory usage. Process list. Below the summary is a list of processes, similar to PSOX but continuously updating. Inside top, you can use several single-key commands. Q, quit top. K, kill a process, you'll be prompted for the PID. P, capital P, sort by CPU usage default. M, capital M, sort by memory usage. T, capital T, sort by running time. H, display help. Top is an excellent tool for real-time diagnostics and quickly identifying what's slowing down your system. 3 H-top, an enhanced interactive process viewer. H-top is a popular alternative to top that offers a more user-friendly, interactive interface with color coding and vertical-horizontal scrolling. It's not usually installed by default, but it's a highly recommended tool. You can typically install it using your distribution's package manager. On Debian/Ubuntu, sudo apt install htop. On Fedora CentOS, sudo dnf install htop. Once installed, simply type htop and press Enter. You'll find it more intuitive to navigate and interact with processes than top, often providing a better visual overview of CPU core usage and memory consumption. Controlling processes and jobs FG/BG kill. Beyond just viewing, you can also control how processes run and manage them if they become unresponsive. 1. Running commands in the background. And, normally, when you execute a command, it runs in the foreground, meaning your terminal prompt won't return until the command finishes. If it's a long-running task, your terminal is tied up. To run a command in the background, simply append an ampersand and to the end of the command. Let's simulate a long-running task. Navigate to your home directory, CD, sleep 30 and the sleep command simply waits for a specified number of seconds. When you run sleep 30, and your prompt will return immediately, and you'll see output similar to 1, 12,345. 1 is the job number, a shell-specific identifier for background processes in your current session. 12,345 is the PID of the sleep process. The sleep command is now running in the background while you can continue using your terminal. 2 listing background jobs. To see what processes are running in the background managed by your current shell session, use the jobs command. Jobs, you might see 1 plus running sleep 30 and the plus indicates the current job and running shows its status. 3 bringing a job to the foreground, FG. If a background job needs interaction, or if you want to bring it to the foreground to wait for its completion, use FG foreground, followed by the job number. Assuming sleep 30 is job number 1, FG%1, the sleep 30 command will come back to the foreground, and your terminal will be busy until it completes or you stop it. 4. Sending a foreground job to the background, Ctrl+Z and BG. What if you started a long command in the foreground and realized you needed your terminal back? You can pause a running foreground process by pressing Ctrl plus Z. Try it. Sleep 60. Now press Ctrl plus Z. The output will be something like Z. 1 plus stopped sleep 60. The process is now stopped in the background. To resume it in the background, use BG background followed by the job number. BG%1. The process will pick up where it left off, but now running in the background. 5 terminating processes, kill. Sometimes, a program becomes unresponsive, or you need to shut down a background process. The kill command is used to send signals to processes, telling them what to do. The most common signal is to terminate. You need the PID of the process you want to kill. You can get this from PS-aux or top. Let's assume you have a sleep 30 process running with PID 12,345. Kill 12,345. This kill command sends the term terminate, signal number 15 by default. This is a polite request for the process to shut down gracefully. Most well-behaved programs will clean up and exit. What if a program is stubborn and doesn't respond to term? You can send a stronger signal, kill signal number 9. This is the equivalent of pulling the plug. The process is terminated immediately without any chance to clean up. Use kill as a last resort. Kill -9 12,345. 6. Kill all and pkill. Killing by name. If you don't want to look up a PID, kill all allows you to kill all processes with a given name. Kill all Firefox. This command would try to terminate all running processes named Firefox. Be careful with kill all, as it can be indiscriminate if multiple unrelated processes share a common name. pkill is a more sophisticated and flexible version of kill all. It allows you to specify patterns, users, and other criteria to select which processes to kill. For example, to kill processes owned by a specific user, pkill uAlex, or to kill only processes named miscrypt that are running on a specific terminal, pkill tpts/1 miscrypt. These commands are very powerful and should be used with precision to avoid accidentally shutting down critical system processes or other users' work. Taking control of your system. Understanding process management is crucial for efficient system utilization and troubleshooting. You now know how to view a snapshot of processes, PS, monitor them in real-time top, htop, run tasks in the background, and BG, pause and resume Ctrl plus Z, FG, and when necessary, forcibly terminate misbehaving applications, kill all, pkill. These skills will help you maintain a responsive and stable Linux environment. In the next chapter, we'll explore how to customize your command line environment using variables and aliases, making your daily workflow even more efficient and tailored to your needs. Chapter 10, Your System Your Way, Environment Variables and Aliases. By now, you've gained significant control over your Linux system. You can navigate, manage files, search for content, and oversee running processes. These are essential skills, but the command line offers an even deeper level of personalization and efficiency. This chapter will teach you how to customize your shell environment using environment variables to configure how commands behave, and aliases to create your own custom shortcuts for frequently used or lengthy commands. Making these changes permanent will transform your command line experience, molding it to your unique workflow. Variables, storing information in your shell. At its simplest, a variable in a shell is a name that represents a value. Think of it like a temporary placeholder in your computer's memory that stores a piece of information. This information can be a string of text, a number, or even the output of a command. Variables are a fundamental concept in computing and are extensively used in scripting, which we'll cover in the next chapter. You can create a temporary variable in your current shell session like this. MyMessage equals hello, Linux user. That's my_m, ESSAGE equals sign double quote HELLO comma space LINUX space USER double quote. Notice there are no spaces around the equal sign. To see the value stored in a variable, you prefix its name with a $sign. Echo MyMessage. That's ECHO space $my_m ESSAGE. The output will be hello, Linux user. This variable MyMessage is only accessible within your current terminal session. If you close the terminal or open a new one, this variable will be gone. Environment variables. Configuring your shell's world. Environment variables are special types of variables that are inherited by every program and process launched from your shell. They define the environment in which your programs run, influencing their behavior without you needing to explicitly tell each program what to do. They impact how your shell looks, where it searches for commands, what language your system uses, and much more. Let's look at some commonly used environment variables. Home. This variable stores the path to your home directory. Commands and programs often use this to find user-specific configuration files or to create new files in your personal space. Echo home. Output home/username. User. This variable holds your current username. Echo user. Output your username. Path. This is perhaps the most important environment variable. It's a list of directories that your shell searches through to find command executables. When you type ls, your shell doesn't immediately know where ls is located. It checks each directory listed in your path variable in order until it finds the ls program, typically in usr/bin/ls. Echo paths. Output might look like usr/local/sbin/usr/local/bin /usr/sbin/usr/bin/bin/usr/local/games/usr/local/games/snap/bin. Each directory in the path is separated by a colon. Viewing all environment variables, you can see a list of all currently set environment variables using printenv. Printenv. This will produce a long list. You can pipe it through less to scroll, printenv less. Setting environment variables, making them permanent. To make a variable accessible to other programs launched from your shell, you export it. If you want this variable to persist across different terminal sessions or reboots, you need to add the export command to one of the shell's startup files. To temporarily set and export a variable, export mysetting equals enabled. This is export space my_setting equals sign double quote enabLed double quote. This mysetting variable will now be available to any child processes you launch from this terminal. However, it's still temporary for this session. The importance of path. If you download a new program or write your own script and you want to run it simply by typing its name without specifying its full path like /miscript.sh, you need to put the directory containing that program's script into your path. Example, if you save a script in ~miscripts, you can add this directory to your path like this. Export path equals $path $home/miscripts. This command says, take the current path value, add a colon, then add the full path to my miscripts directory and make this new combined string the new path. Now, your shell will also look in miscripts when you type a command. Aliases. Your personal command shortcuts. An alias is a shortcut that allows you to replace a long or frequently used command with a shorter, easier to remember name. Aliases are defined within your shell and are processed before the shell tries to find an actual command program. Viewing existing aliases, many Linux distributions set up useful aliases by default. To see them, alias. alias. You might see aliases like alias ls color equals auto, makes ls output colorful. Alias ll, lslf, a common shortcut for a detailed, classified listing. Creating your own aliases. An alias is created by assigning a new name to an existing command or sequence of commands. Syntax. Alias new name equals original command options arguments. Let's create an alias for a detailed listing that you find useful. Alias mylist equals lslhf. That's alias space mylist equals sign, single quote, ls space dash lhf single quote. Now, instead of typing lslhf, you can simply type mylist and press enter. Here are some other practical alias examples. Alias c equals clear, clears the terminal screen. Alias myp equals ip a grep inet grep v 127.0.0.1 awk, print $2. Cut d f1, a quick way to see your IP address using multiple commands. We'll touch on awk and cut later, but this shows the power of combining things into an alias. Alias update equals sudo apt update and sudo apt upgrade. For Debian/Ubuntu users, update system packages. Alias ll equals lslog group directories first. A very detailed long listing, grouping directories first. Removing an alias. To remove an alias from your current session, unalias mylist. That's UNALIAS space MYLIST. Shell configuration files, making changes permanent. Both environment variables and aliases are temporary by default. They only last for the current shell session. To make them permanent, so they are set every time you open a new terminal, you need to add them to specific shell configuration files located in your home directory. These files are hidden, they start with A. So you'll need LSA to see them. On most Linux systems that use the bash shell, which is the default for most users, the primary configuration files are bashrc. This file is read and executed every time you open a new interactive bash shell session, like a new terminal window. This is the best place to put your aliases and local shell functions, and any environment variables you want to set specifically for interactive use. Profile. This file is read when you log into your system, either graphically or via a login shell, like connecting via SSH. It's typically used for setting up global environment variables that should apply to all programs, not just your shell. Often, profile will source bashrc, your bashrc file. Bash profile. On some systems, this file is read instead of profile when you start a login shell. If both bash profile and profile exist, bash profile usually takes precedence. Many users configure their bash profile to source, bashrc, so they only need to maintain one file for common shell configurations. How to edit and apply changes. To add your aliases or environment variables permanently, open the file. Use a text editor like Nano, which is simple and great for beginners, to open bashrc. Nano bashrc. Add your lines, scroll to the bottom of the file, and add your export commands and alias definitions. Example, export editor equals nan. Export custom path equals $path, /usr/local/mybin. Alias clr equals clear. Alias migrep equals grep-in. Save and exit. In Nano, usually press Ctrl+O, Ctrl-O to write out the changes, then Enter to confirm the file name, and Ctrl+X, Ctrl-X to exit. Apply changes. For the changes to take effect in your current terminal session, you need to source the file. This tells the shell to reread and execute the commands in the file. Source, bashrc. Or you can simply close and reopen your terminal. From now on, every time you open a new terminal, your custom aliases and variables will be ready to use. Building your custom environment. By understanding and utilizing environment variables and aliases, you're not just executing commands. You're actively shaping how your shell behaves and how it assists you. Customizing your prompt, adding convenient shortcuts, and extending your command search path are all ways you can tailor your Linux experience to be more efficient, reflective of your preferences, and optimized for your daily tasks. This transformation from a generic shell to a personalized powerhouse is a hallmark of a true power user. In the next chapter, we'll take this customization a step further by diving into the fundamentals of shell scripting, allowing you to automate complex sequences of commands and turn repetitive chores into single command executions. Chapter 11, Scripting Fundamentals, Automating Tasks with Bash. You've learned to navigate, manage files, monitor processes, and even customize your shell. These are powerful skills, but imagine needing to perform a sequence of 10 commands every day, or wanting to automate a complex task that combines several utilities. Typing them repeatedly is not efficient. This is where shell scripting comes in. Shell scripting is the art of writing a series of commands and instructions in a plain text file, which the shell can then execute automatically. It turns repetitive chores into single command executions, saving you time, reducing errors, and unlocking a new level of command line power. This chapter will introduce you to the fundamentals of bash scripting, the most common shell for Linux. What is a shell script? At its heart, a shell script is simply a text file containing a list of commands, just like the ones you type at the command prompt, executed in sequence. The shell reads the script line by line and executes each command. The shebang line. Every shell script should begin with a special line called the shebang, which tells the system which interpreter to use for executing the script. For bash scripts, this line is typically hash bin bash. That's a hash followed immediately by an exclamation mark, then a space followed by bin bash. This line means, hey operating system, when you run this script, use the bash interpreter located at bin bash to execute the commands within this file, making your script executable. By default, when you create a new text file, it doesn't have execute permissions. You need to explicitly grant this permission using the chmod command, change mode, which you'll explore further in Chapter 13 on permissions. Let's create our first simple script. In your home directory, create a new file named helloscript.sh using your favorite text editor, like Nano helloscript.sh. Inside Nano, type the following two lines, hash, bin bash, echo hello from your first script. Remember to type that first line, then the echo command as you've seen it before. Save the file and exit your editor. Now, to make it executable, type chmod plus x helloscript.sh. That's chmod space plus x space hello underscore script.sh. Executing your script. To run your script, you need to tell the shell where to find it. Since it's in your current directory, you prefix its name with which means in the current directory. /helloscript.sh. That's /hello underscore script.sh. You should see the output, hello from your first script, congratulations. You've just created and executed your first bash script. Basic scripting elements. Comments. Comments are lines in your script that are ignored by the shell. They are solely for human readers, making your script easier to understand and maintain. Any line starting with a hash symbol hash, unless it's the shebang line, is treated as a comment. Example, hash this is a comment. It explains what the next command does. Echo, this command will be executed. Variables in scripts. Variables in scripts work just like the temporary shell variables you saw in Chapter 10. They store values that can be used and manipulated throughout your script. No export is needed unless you specifically want the variable to be available to other commands or child scripts that your script might launch. Example, hash, bin bash. My name equals Alex. Toddy equals $, date plus %y%m%d. Echo hello, myName. Today is TODYDAT. Note, date plus %y%m%d is command substitution. Date command's output is assigned to TODAYDATE variable. Input from the user. Read. The read command allows your script to take input directly from the user. It pauses the script execution until the user types something and presses enter. Example, hash, bin bash. Echo, what is your name? Read username. Echo, nice to meet you, username. Positional parameters. When you run a script, you can pass arguments to it. These arguments become special variables within the script, known as positional parameters. $0, the name of the script itself. $1, the first argument passed to the script. $2, the second argument, and so on. At $, represents all arguments as separate strings. Hash, the number of arguments passed to the script. Let's create a script named greetsh, nano greetsh. Bin bash, echo script name, $0. Echo first argument, $1. Echo second argument, $2. Echo all arguments. Echo number of arguments. Save, exit, and make it executable. chmod plus x greetsh. Now run it with some arguments. /greetsh Alice Bob. Output script name, /greetsh. First argument, Alice. Second argument, Bob. All arguments, Alice Bob. Number of arguments, 2. Positional parameters are crucial for writing flexible scripts that can operate on different inputs. Control flow, making decisions and repeating actions. Bash scripting allows you to control the flow of execution, making your scripts intelligent and dynamic. 1. Conditional statements, if-else, elif. If statements allow your script to make decisions based on whether a condition is true or false. The basic syntax involves an if block, followed by a then block, if the condition is true, and an phi to close the if statement. Conditions are usually enclosed in single square brackets or double square brackets. Common conditions, tests. Condition, classic Unix test command syntax. Condition, enhanced bash feature, more flexible. F file. True if file exists and is a regular file. DDIR, true if dir exists and is a directory. Z-string, true if string has 0 length is empty. N-string, true if string has non-zero length. String 1 equals string 2, true if strings are equal. Number 1 ek number 2, true if numbers are numerically equal, ni for not equal, gt for greater than, lt for less than, etc. Let's modify greet.sh to check if a name was provided. Nano greetuser.sh. Bin bash. If z $1, then echo usage, $0 name. Else, echo hello $1. Phi, save, make executable and run. Slash greetuser.sh, no argument. Output, usage, slash greetuser.sh name. Slash greetuser.sh Charlie. Output, hello Charlie. The else branch executes if the if condition is false. You can also use a if else if for multiple conditions. 2 loops, repeating actions. Loops allow you to execute a block of code multiple times. For loop, A for loop iterates over a list of items, executing the commands inside the loop for each item. Example, processing multiple files with a for loop. Create some empty files using touch file, txt file 2, txt file 3, txt. Now create a script process files sh. Nano process files sh. Bin bash. For file n txt, do. Echo processing file. WCL file. Done. That's FOR space FILE space IN space asterisk dot TXT semicolon DO. Then on the next line, echo and WCL commands. Finally, DONE to finish the loop. Save, make executable and run. Slash process files sh. Output, processing file 1 txt. File 1 txt. Processing file 2 txt. 0 file 2 txt. Processing file 3 txt. 0 file 3 txt. The for loop iterated over each file name ending with txt in the current directory, assigned it to the file variable, and then executed the commands inside the do. Done block. While loop, a while loop continues to execute a block of commands as long as a condition remains true. Example, counting down from 5. Nano countdown sh. Bin bash. Count equals 5. While count gt0, do. Echo count. Count equals $count 1. Sleep 1. Done. Echo liftoff. Arithmetic in bash uses. A syntax. Save, make executable and run. Slash countdown sh. You'll see a countdown from 5 with a 1-second pause between each number, then liftoff. Simple scripting examples. Let's combine these concepts into practical examples you might use. 1. Daily backup script. This script could create a timestamped archive of your important documents. Nano daily backup sh. Bin bash. Hash this script creates a timestamped backup of my documents folder. Backup dir equals $home/backups. Source dir equals $home/documents. Timestamp equals $. Date plus %y%, m%d%h%, m%s. Archive name equals documents backup $timestamp targz. Hash create the backup directory if it doesn't exist. mkdir p basicopdir. Hash create the targz archive. Echo creating backup of sourcdir. Tar czvf backup dir /$archive name sourcdir. Echo backup complete. Backup dir /$archive name. Hash optional. Remove backups older than 7 days. Echo removing old backups older than 7 days. Find basicopdir type fname targz mtime plus 7 delete. Echo done cleaning old backups. Make it executable and try running it. You'll have a new date-stamped backup in your ~backups directory. 2. Bulk renaming script. Imagine you downloaded 100 images named img1234.jpg, img1235.jpg, and you want them to be vacation001.jpg, vacation002.jpg, etc. This script renames them sequentially. Nano rename images sh. Bin bash. Hash this script renames img.jpg files to vacation.jpg sequentially. Hash run this script in the directory containing the images. Count equals 1. For image and img.jpg. Do. Hash construct the new name with leading zeros. New name equals $. Print vacation%03d.jpg. Count. Echo renaming image to any WNAME. MV image, any WNAME. Count equals $count plus 1. Done. Echo renaming complete. Before running this, create some dummy img.jpg files like touch img00, 1.jpg, img00, 2.jpg. This script introduces print for formatted output, specifically to get those leading zeros. The power of automation. Shell scripting is one of the most practical and immediately rewarding skills you can develop on the command line. It moves you from merely using commands to programming your shell to perform complex, automated tasks. The ability to write a script that does your bidding will save you hours of manual work and open up new possibilities for system management, data processing, and personal productivity. In the next chapter, we'll shift our focus to an increasingly crucial area of computing: networking. You'll learn essential command line tools to interact with networks, diagnose connectivity issues, and manage remote systems. Chapter 12, Network Ninja, Basic Network Commands. In today's interconnected world, understanding how your computer interacts with networks is more critical than ever. Whether you're troubleshooting your internet connection, accessing files on a remote server, or deploying applications in the cloud, the Linux command line provides powerful tools for network diagnostics and remote communication. This chapter will introduce you to essential network commands, transforming you into a basic network ninja. Testing connectivity, ping. The ping command is one of the simplest yet most fundamental network utilities. It's used to test the reachability of a host on an internet protocol, IP network, and to measure the round-trip time for messages sent from the originating host to a destination computer. Think of it as sending a sonar pulse and listening for the echo. Syntax: ping destination host. The destination host can be an IP address, e.g., 8.8.8.8 for Google's public DNS server, or a hostname, e.g., google.com. Let's try to ping Google's website, pinggoogle.com. That's ping space google.com. You'll see output similar to this, continuously repeating. Pinggoogle.com, 142.250.72.142, 56, 84 bytes of data. 64 bytes from 142.250.72.142. ICMSEC equals 1 TTL equals 118 time equals 15.1 ms. 64 bytes from 142.250.72.142. ICMSEC equals 2 TTL equals 118 time equals 14.9 ms. ICMSEC, the sequence number of the ICMP packet, TTL. Time to live, indicating how many network hops the packet can take before being discarded. Time, the round-trip time in milliseconds, ms, showing how fast the connection is. Ping will continue indefinitely until you stop it by pressing Ctrl+C tips for ping. To send a specific number of pings, e.g., 5 times, use the C option. Ping C5 google.com. If ping fails, destination host unreachable, or request timed out, it indicates a network connectivity problem between your computer and the destination. This could be your Wi-Fi, router, internet service provider, or the destination's server itself. Local network information, IP and SS. To manage and troubleshoot your own network connections, you need to know your computer's IP address, network interfaces, and open network ports. While older commands like ifconfig and netstat are still around, the more modern and powerful tools are IP and SS. 1. IP, displaying network interfaces and addresses. The IP command is a comprehensive tool for managing routing, devices, policy routing, and tunnels. One of its most common uses is to check your network interfaces and IP addresses. To display information about all your network interfaces, IP addr show, IP space ADDR space SHOW. You'll see several sections, one for each network interface. Common interface names include LOW, the loopback interface used for internal communication on your computer, typically 127.0.0.1. ETH0 or EMP XSY, wired Ethernet connection. WLAN 0 or WLP XSY, wireless Wi-Fi connection. Look for lines starting with INET for IP4 addresses or INET6 for IP6 addresses within your ETH0 or WLAN 0 section. For example, INET 168.1.100/24 BRD 192.168.1.255 scope global dynamic WLP30. This shows that your Wi-Fi interface, WLP30, has the IP4 address 192.168.1.100. The 24 refers to the network mask. You can also use this command to display your routing table, IP route show. This command shows how your computer forwards network traffic, indicating your default gateway, usually your router. 2. SS, socket statistics. The SS command is used to dump socket statistics, showing active network connections and listening ports. This is incredibly useful for seeing which applications are communicating over the network and which services are waiting for incoming connections. This command is a modern replacement for Netstat. To show all listening TCP ports, SSLTN, SS space dash LTN. L listen show listening sockets. T TCP show TCP connections. N numeric don't try to look up service names faster. You might see things like listen 0 128 0.0.0.0 colon 22 0.0.0.0 asterisk. This indicates that a service is listening on port 22, SSH, on all available IP4 addresses, 0.0.0.0. To show all established TCP connections, SS at A. All show all sockets, listening and non-listening. T. TCP. You'll see connections to web servers, mail servers, and other services. Remote access. SSA. Secure Shell, SSH, is the workhorse of remote system administration. It provides a secure way to connect to a remote computer over an unsecured network. Once connected, it gives you a command line interface to the remote system, just as if you were sitting in front of it. It's how system administrators manage servers around the world. Syntax. SSH username at hostname. To connect to a remote server with the IP address 192.168.1.200 using the username admin. SSH admin at 192.168.1.200. That's SSH space a DMIN at sign 192.168.1.200. The first time you connect to a new host, SSH will ask you to confirm its authenticity to protect against man-in-the-middle attacks. After confirming, you'll be prompted for the user's password on the remote system. Once authenticated, you will be presented with a command prompt on the remote machine. You can then run any command as if you were locally on that system. To exit the SSH session, simply type exit and press enter. SSH keys, brief mention. For managing multiple servers securely and without repeatedly typing passwords, SSH supports public key authentication using cryptographic key pairs. This is a more advanced topic but essential for efficient server management. Secure File Transfer, SCP. While SSH lets you execute commands remotely, SCP, Secure Copy, allows you to securely copy files between your local computer and a remote one, or even between two remote computers. It uses SSH for data transfer and authentication, providing the same level of security. Syntax for copying a local file to a remote server. SCP localfile path username at remote host, remote path. Let's copy your mynotesTXT file from your home directory to the remote server's home directory. SCP:/mynotesTXT admin at 192.168.1.200. tilde. That's SCP space tilde slash my_notes.tx. T space a DMIN at sign 192.168.1.200 colon tilde. You'll be prompted for the password for admin on the remote host. The on the remote path expands to the admin user's home directory on the remote system. To copy a file from a remote server to your local machine. SCP username at remote host, remote file path local path. To copy remotelog.txt from the remote server's var/log/directory to your current local directory. SCP admin at 192.168.1.200 /var/log/remotelog.txt. The dot at the end means the current local directory. Downloading files. wget and curl. When you need to download files directly from the internet using the command line, wget and curl are your primary tools. 1. wget. Non-interactive network downloader. wget, WebGAT, is designed for non-interactive downloading of files from web servers. It works well for simple HTTP, HTTPS, and FTP downloads, and can even resume interrupted downloads. To download a file from a URL, wget https example.com/sumfilezip. That's wget space https://example.com/somefile.zip. The file sumfilezip will be downloaded to your current directory. 2. Curl, command line tool for transferring data. Curl is an incredibly versatile tool for transferring data with URLs. While wget is primarily a downloader, curl can send and receive data using a vast array of network protocols. It's often used by developers to interact with web APIs. To download a file with curl, you typically use the capital O option to save the output to a file with the same name as the remote file, or lowercase o to specify a custom local file name. Curl https example.com/anotherfaltargz saves as anotherfaltargz. Curl mydownloadtxt https example.com/textcontenthtml saves content as mydownloadtxt. Curl is especially powerful for interacting with web services. For instance, curl https api.github.com/users/octocat. This command would output a JSON JavaScript object notation formatted response from the GitHub API about the Octocat user directly to your terminal. The network at your fingertips. You've taken a significant step into the world of command line networking. You can now test connectivity, ping, identify your IP address and open ports, IP, SS, connect to and manage remote servers, SSH, transfer files securely, SCP, and download content from the internet, wget, curl. These commands are indispensable for anyone working in a networked environment, providing you with a powerful toolkit for diagnostics, administration, and data transfer. In our final essential chapter, we will address user management and permissions, two critical aspects of Linux security and multi-user environments, ensuring you understand how to keep your system secure and well-controlled. Chapter 13, User Management and Permissions, Keeping Your System Secure. As you've progressed through this book, you've gained increasing control over your Linux system. With great power comes great responsibility, especially regarding system security. Linux, by nature, is a multi-user operating system, designed to allow multiple individuals to use the same machine or server simultaneously and securely. This capability relies heavily on a robust permission system and well-defined user and group management. This chapter will demystify these crucial concepts, helping you understand how to control who can access and modify files, and how to execute commands with elevated privileges when necessary. Users and groups, identity and access control. Every process and file on a Linux system is associated with a user and a group. This forms the basis of its security model. Users. Each person or system service interacting with the system has a unique user account, identified by a username, e.g., Alex, root, www.data. The root user. This is the superuser account with ultimate administrative privileges. The root user can do anything on the system, which is why it's crucial to use the root account with extreme caution and only when necessary. Regular users. Your personal user account, Alex in our examples, is a regular user. Regular users typically have full control over files in their own home directory, but limited access to system-wide files. System users. Many services run under their own dedicated user accounts, e.g., www.data for a web server, bind for a DNS server. These accounts have limited privileges, reducing the risk if the service is compromised. Groups. Groups are collections of users. Permissions can be assigned to a group, and all members of that group inherit those permissions. This simplifies managing access for multiple users to shared resources. For example, if several users need access to a specific directory of shared project files, you can create a group, add those users to it, and then assign permissions to the group for that directory. Identifying your user and groups. To find out your current username, who am I? To see your user ID, UID, group ID, GID, and all groups you belong to, ID. To see who else is currently logged in, W or who. Permissions deep dive. RWX in octal modes. You've already seen the RWXRXRX strings in LSL output. Let's break them down definitively. Each permission string is comprised of 11 characters. 1. File type first character, D, directory. Irregular file. L, symbolic link. Among others like C for character device, B for block device. 2 permissions for user, group, and others. Next 9 characters. These 9 characters are divided into 3 sets of 3, representing the permissions for the owner, the group, and others, everyone else. Each position can be R read, W write, X execute, or a hyphen, no permission. Read R. For a file, allows viewing the contents of the file. For a directory, allows listing the contents of the directory with ls. Write W, for a file, allows modifying, saving, or deleting the file. For a directory, allows creating, deleting, or renaming files within that directory. Execute X, for a file, allows running the file as a program or script. For a directory, allows entering or CDing into the directory. Without execute permission, you can't access files inside it, even if you have read permission. Example RWXRXRX explained, first RWX, owner has read, write, and execute permissions. Second RX, group has read and execute permissions, but not write. Third RX, others have read and execute permissions, but not write. Changing permissions, chmod. The chmod command, change mode, is used to change the permissions of files and directories. There are 2 main ways to specify permissions with chmod: symbolic mode and octal numeric mode. 1. Symbolic mode, user-friendly and explicit. Symbolic mode uses letters to represent who gets what permission. Who, U user owner, G group, O others, A all, U go. Action plus add permission, remove permission, equals set permission exactly. Permission, RWX. Examples, navigate to your home directory for practice. Make a script executable, you have HelloScript.sh from chapter 11. To ensure only you can execute it, chmod U plus X HelloScript.sh. U for user, plus to add, X for execute. Remove write permission for others. Prevent anyone else from modifying your mynotesTxt. chmod OW mynotesTxt. O for others, to remove, W for write. Set specific permissions for all. Make a file read-only for everyone. chmod A equals R mynotesTxt. A for all equals to set exactly, R for read. Grant write for group and others too, and execute for directory. chmod go plus W mishared folder. G for group, O for others, plus to add, W for write. 2. Octal numeric mode, concise and common. Octal mode uses 3 digits, 0 to 7, to represent permissions. Each digit is a sum of values for R, W, and X. R read equals 4. W write 2. X execute equals 1. No permission equals 0. You sum these values for each of the 3 permission sets: user, group, others. Common octal values. 7 RWX equals 4 plus 2 plus 1 read, write, execute. 6 RW equals 4 plus 2 plus 0 read, write. 5 RX equals 4 plus 0 plus 1 read, execute. 4 R equals 4 plus 0 plus 0 read only. Equals 0 plus 0 plus 0, no permissions. Examples: chmod 755 filename, owner, 7 RWX. Group 5 RX. Others 5 RX. This is a common permission for executable scripts and directories, where others should be able to read and enter, but not modify. chmod 644 filename, owner, 6 RW. Group 4R. Others 4R. This is a common permission for regular files, allowing the owner to read-write and everyone else to read. Make a script executable numeric. chmod 700 HelloScript.sh. 7 for owner read, write, execute, 0 for group and others no access. This is very secure for personal scripts. Changing ownership. Chown and chgrp. While chmod changes who can do what with a file, chown change owner modifies who owns the file, and chgrp, change group, modifies which group the file belongs to. You typically need administrative sudo privileges to use these commands on files you don't own. Chown change owner, chown new owner file name. Sudo chown alex important document txt. Changes owner of important document txt to alex. chgrp change group. chgrp new group file name. Sudo chgrp developers project files / changes group of project files directory to developers. Changing both owner and group. Chown new owner, new group file name. Sudo chown alex, staff shared report odds, to apply changes recursively to all files and subdirectories within a directory. Use the R option with both chown and chgrp. Superuser power, sudo and su. Most of the time, you will operate as a regular user. However, many system administration tasks require elevated privileges, such as installing software, modifying system configuration files, or managing other users. 1. Sudo. Execute command as another user, typically root. Sudo superuser do is the preferred way to execute commands with elevated privileges. It temporarily grants you root permissions for a single command, provided your user account is in the sudo group and you know your own password. This is much safer than routinely logging in as root. Sudo apt update. This will run the apt update command as the root user, which is necessary to update package lists. When you run sudo for the first time in a session, it will ask for your user password, not the root password. Once you enter it successfully, sudo will remember it for a short period, typically 5 to 15 minutes, allowing you to run subsequent sudo commands without re-entering the password. Caveats with sudo: always be careful. Sudo gives you the power to do anything, including accidentally breaking your system. Double-check commands before running them with sudo. As discussed in Chapter 4, sudo rmrf is the most dangerous command. Never type it unless you know exactly what you're doing, which for 99.9% of situations you won't. 2. Su, switch user. The su command, substitute user or switch user, allows you to switch to another user account within the current terminal session. If no username is specified, it defaults to root. Su su space dash. Using su logs you into the root account as if you had logged in directly, loading root's environment variables and home directory. It will ask for the root user's password. You'll know your root because your command prompt will typically change from to exit the root shell and return to your previous user, type exit. Use su less frequently than sudo. Sudo is safer because it requires your password, logs your actions to system logs, and only grants elevated privileges for a single command. Su gives you continuous root access until you exit, making it easier to accidentally make broad system changes. A secure foundation. Understanding users, groups, permissions, and the proper use of sudo is fundamental to maintaining a secure and functional Linux system. These concepts dictate who can do what, ensuring data integrity and system stability in a multi-user environment. By mastering these permissions, you can protect your own files, secure your system from unauthorized access, and confidently perform administrative tasks. With this chapter, you now have a comprehensive understanding of the core functionalities of the Linux command line necessary for daily use and system interaction. You've built a robust foundation. In our final chapter, Beyond the Basics, we'll discuss where to go next, introducing more advanced tools and concepts, and providing resources for your continued journey as a Linux power user. Chapter 14, Beyond the Basics, where to go next. Congratulations, you've reached the final chapter of Beyond the Mouse. Reflect for a moment on the journey you've embarked on. You started with a blank terminal screen, perhaps a sense of apprehension, and now you can navigate complex file structures, create scripts to automate tasks, manage running processes, inspect network connections, and understand the intricate web of users and permissions. You are no longer just a user. You are a proficient operator, capable of harnessing the true power of your Linux system directly from the command line. This book has equipped you with the essential skills, the foundation upon which you can build a towering edifice of Linux mastery. But the world of the command line is vast, ever-evolving, and constantly offering new tools and challenges. This final chapter will serve as a roadmap for your continued learning, pointing you towards key areas, advanced tools, and strategies for expanding your expertise. Tools for text editing from the command line. while cat and less are great for viewing. Eventually, you'll need to edit text files directly from the command line, especially when working on remote servers without a graphical interface. Nano, the friendly text editor. Nano is a simple, intuitive, and beginner-friendly text editor. It displays common commands at the bottom of the screen, making it easy to learn. It's excellent for quick edits and for those new to command line editors. To open a file for editing, Nano filename.txt. You'll then see instructions inside Nano, typically Ctrl-O to save, Ctrl-X to exit. Vim or Roman 6, the powerful, steep learning curve editor. Vim, and its older counterpart Roman 6, is an incredibly powerful and efficient text editor, revered by experienced users for its speed and extensibility once mastered. However, it has a notoriously steep learning curve as it operates in different modes, e.g., insert mode for typing, normal mode for commands. To open a file, Vim filename.txt, you'll immediately be in normal mode. Press I to enter insert mode to start typing. Press ESC to go back to normal mode. Type WQ and press enter to save and quit. While Nano is great for beginners, learning Vim can significantly boost your productivity for complex editing tasks and is a valuable skill for any serious Linux user or developer. Many distributions now use Roman 6 as an alias for Vim for compatibility. Deeper automation, scheduling tasks with cron. You learn to write bash scripts. Imagine if those scripts could run automatically at scheduled times daily, weekly, or even every minute. This is where cron comes in. Cron is a time-based job scheduler in Unix-like operating systems. It enables users to schedule commands or scripts to run automatically at a specified date and time. These scheduled tasks are called cron jobs. You manage your own cron jobs using the crontab command. To open your personal crontab file for editing, it will open in your default command line editor, often Nano or Vim. Crontab E. To list your current cron jobs, crontab L. A common cron job entry looks like this, each field separated by a space. Minute hour day of month month of year day of week command to execute. Example, to run your daily backup sh script, located in your home directory, every day at 3 o'clock a.m. 03/home/ your username /daily backup sh. The asterisks mean every unit. So, every day of the month, every month of the year, every day of the week. Cron is essential for automating backups, cleaning up temporary files, generating reports, and performing routine system maintenance. Beyond the shell, package management. While we touched upon package managers briefly, they are central to installing, updating, and removing software on your Linux system. Understanding your distribution's chosen package manager is crucial. Debian/Ubuntu apt sudo apt update updates the list of available packages. Sudo apt upgrade upgrades installed packages to their latest versions. Sudo apt install package name installs a new package. Sudo apt remove package name uninstalls a package. Sudo apt search keyword searches for packages. Fedora CentOS DNF sudo DNF update updates everything. Sudo DNF install package name installs a package. Arch Linux pacman sudo pacman-cu syncs and updates. Sudo pacman-s package name installs a package. These commands make software management incredibly easy and are fundamental to keeping your system healthy and equipped with the tools you need. Version control with Git. For anyone serious about development, writing scripts, or even managing critical configuration files, Git, the distributed version control system, is indispensable. Git allows you to track changes to your files, revert to previous versions, collaborate with others, and manage different branches of a project. It's widely used for software development, but is gaining popularity for managing any evolving set of text files. Git init initializes a new Git repository. Git add file name stages changes for commit. Git commit m commit message saves the staged changes. Git status shows the state of your working directory. Git log shows commit history. Git clone repository URL copies a remote repository to your local machine. Learning Git is a journey in itself, but it's a highly recommended next step for managing your personal projects and collaborating effectively. Virtualization and containers, Docker. Modern development and deployment often involve virtualization and containers. Virtualization, e.g., VirtualBox (KVM), allows you to run multiple isolated operating systems on a single physical machine. This is great for testing new Linux distributions or isolating development environments. Containers, e.g., Docker, provide a lightweight, isolated environment for running applications. They package an application with all its dependencies into a single unit, ensuring it runs consistently across different environments. Docker has become a dominant force in cloud computing and DevOps. The Docker command line utility is used to manage Docker containers, images, networks, and volumes. Learning Docker commands like docker run, docker build, and docker ps will open up vast possibilities for application deployment and development workflows. Exploring other shells, ZSH, fish. While Bash is the standard and what we primarily covered, other powerful shells offer different features and user experiences. ZSH, Z shell, a superset of Bash, offering advanced features like improved tab completion, powerful globbing, pattern matching, and themes. Frameworks like OhmyZSH make it easy to customize. Fish, friendly interactive shell, designed with user-friendliness in mind, offering syntax highlighting, auto-completion suggestions, and a powerful scripting language all out of the box. Experimenting with different shells, like using CHSH, change shell, can transform your interactive command line experience. Your continuous learning journey. The true power of the Linux command line isn't just in knowing individual commands, but in understanding how to combine them, automate them, and integrate them into your workflow. Here are some strategies for continued learning. Keep practicing. The best way to learn is by doing. Set yourself small challenges. Automate a daily task, write a script to organize your downloads, or analyze a log file. Read the man pages. For any command you learn, type man command name. This is the definitive manual for that command. Start by reading the name and synopsis sections, then skim for options that sound useful. Explore Stack Overflow and online guides. Websites like Stack Overflow, Ask Ubuntu, and sites dedicated to Linux tutorials are invaluable resources for solving specific problems and discovering new techniques. Join online communities. Engage with Linux user groups or forums. Learning from others and teaching what you know, even if it's just repeating what you've learned to someone else, solidifies your understanding. Contribute to open source. Start by exploring open source projects. You don't have to be a developer. Contributing to documentation, testing, or reporting bugs can deepen your understanding. Read more books. Dive into more specialized books on Bash scripting, system administration, or specific utilities like awk, and said powerful text manipulation tools. You've embarked on an exciting journey. The command line is a tool that empowers you, giving you unparalleled control and insight into your computer. As you continue to explore, automate, and innovate beyond the mouse, you will find that the possibilities are truly limitless. The future of computing is built on automation, and you now have the fundamental skills to be a part of it. Good luck and happy commanding.